So having gone through this procedure, it should be clear to you all now that cumulative production is basically an integral of your flow rate. Now we went through this integration analytically. So this is an analytical integration because it's easy to evaluate the integral of this function. In some cases, the expression for Q will be very complicated. It could be some cubic spline or some error function, and in some cases, you cannot integrate it analytically. So what do? Then you use numerical integration. And that's why we're talking about numerical integration. It is an approximation of the area under a curve. So it's a way to compute your integral numerically. So instead of programming the equation for QP in Python, we can actually numerically find the area under the curve of flow rates against time. So find the area under the curve, and that will be the cumulative production. And to find that area, we can use the trapezoidal rule, which you all have learned before. And the trapezoidal rule is illustrated here. So this is the function with some sinusoidal function, and you want to find the area under that function. How do you do it? Draw a bunch of trapezoids under the curve. Why are you drawing trapezoids? So that you can approximate the trend in the curve, right? So it's multiple straight lines trying to mimic your sinusoidal curves. See, in some cases the line goes below the curve, in some cases it goes above the curve. You're just connecting a bunch of points. Right? Literally what you do is you distribute points in the x-axis and then draw it all the way to the curve, and then connect the points of the function at those points. And so, because you've drawn a bunch of trapezoids, to find the area under the curve, sum up the areas of each of these trapezoids. So this area 1, area 2, area 3, and so on. Sum up the areas under the curve, and what you have is the integral of that function. And that's what the trapezoidal rule does. It's a definite integral. Here is going between a and b, where this is a, this is b, right? So between a and b, you have a bunch of points, right? Which corresponds to a bunch of trapezoids. So you go from n equals 0 to n minus 1. Basically, you're counting all these trapezoids. And then you use the area of a trapezoid, which is half a plus b times height, right? So the trapezoid is drawn standing. So this is actually the height, which is the change in x, because this is your x-axis. So that's why you see delta x here. So the change in x is the height, which is outside. And then you need the function at the 2 points. The function value here, the function value here. That's your a plus b. And so that's why it's function at n plus function at n plus 1. And this is one trapezoid. And then you do the summation, and you go from the number of trapezoids from 1 to the last trapezoid. Here there's certainly to go from index 0 to n minus 1. Same as going from 1 to n, right? And that's your trapezoidal rule. And that's what you will be programming to. So given any function, I can actually give you values corresponding to these points. And then you will integrate it using this trapezoidal rule, sum of trapezoids, and you get the area under the curve. So this is some description of what I explained right here. Partition the area under the curve into strips of trapezoids. Sum up the areas of each of these trapezoids after calculating it. It's very commonly used in petroleum engineering. And now we move on to accuracy, precision, and errors. Just definition of terms. And I like to ask quiz questions on this. So very important to understand what's on this slide and the following slide. So accuracy refers to how closely an approximation, a value, agrees with the true or exact value. So this is the key, the true value, which is the exact value. So if this is the true value and your estimate is here, very close to it, then the accuracy is high. So you have a numerical estimate, you have the true value. Accuracy is how closely your estimate agrees with the true value. An example is to measure the closeness of the exponential decline rate equation to the true value. And in this case, what is the true value of flow rate? It's actually the observed historical flow rate. So we have gauges at the wellhead measuring the flow rate. When you use the exponential decline equation, you fit it through the historical data sets, you can make a prediction from the exponential model. How closely does the prediction match the observed historical production rate? That is the accuracy of the decline model. So if we go back all the way here, this is an exponential model, right? Actually, it was a logarithmic trend line. This is not your decline curve model. This is your logarithmic trend line, right? How closely this red line matches the observed historical rate, which is from the well field, meaning these rates were obtained from flow meters installed at the top of this well on the North Sea. But that is the true value. How closely this approximation matches the true value is accuracy. Very important. And that's different from precision. In precision, you don't know the true value. So it's just two approximations. So precision is how closely values agree with each other. So I make a prediction, say in one time step, and in the next time step, I'm predicting the value is here. Precision is how closely these two values are. And this is very important in iterative algorithms, meaning you have a loop, say a loop from 1 to 10. Let's say I is 1 to 10, and then in each loop you increment I by a certain value. Say I equals, let me write it better. So you have a loop, and then you have I as a variable which is increasing from 1 all the way to 10. And then within this loop you do some calculations. At the end you have, say, an x, which is a function of I and something else. So you're looking at the value of x, and you can actually plot out the value of x. And if that value is still changing a lot, then it's not yet precise. If that value is flattening out to some constant value, so that value no more changes through time, then the precision is high. So the important thing is, with precision, there is no knowledge of the true or exact value. You're just comparing two approximate values. So you're comparing two approximations, and there is no concept of having the true value. When you're comparing your single estimate to the true value, then you're talking about accuracy. When you're comparing two estimates, you're talking about precision. So an example is given here. The measure of the closeness of the analytical integration of the exponential decline rate equation to the numerical integration of the same decline rate equation could be described as the precision. And this is a trick example, right? It's a tricky example, and I can use this to come up with a trick question, because you will think, oh, it's analytical integration, then it's exact. Well, it's analytical integration of what? Exponential decline rate equation. Is the decline rate equation, is it the true value? No. What is the true value? I gave you the true value here, right? The true value is the historical production rate. Your exponential decline rate is an approximate solution, is an approximation of the actual or true value. So integrating this approximate value doesn't give you the true value, right? So even though you are using an exact integration, the model is fundamentally approximate. So this is an estimate, estimate 1. The second estimate, you're using numerical integration of the same decline rate equation, right? That's another estimate. It's not the true value. Neither of these two are the true values, and that's why it's precision. It's very important to note that the difference between accuracy and precision is true value. In accuracy, you compare to the true value, so it's accuracy. In precision, you compare two estimates. So this was just a little tricky in the sense that one estimate came from analytical integration, the other estimate came from numerical integration, neither of which has the true value. So it is precision. Again, good trick questions can be constructed on this. And I'll finish up the remaining slides in the last video.